So I will graph them in two different colors so you understand that they are not connected and you cannot extend them. So -2, -8, 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, right here. -1, -7, which is a full point. How do I know it's a full point? Because it has a bracket here. So that is this line, done. And now for the other one, at -1, I'm sorry, -1, -7 is right there. Sorry, I went too far. My apologies. I went to 0 for no reason. Okay, so now we have -1, +3, 1, 2, 3, with an open point. So you see at this, for x equals -1, there is only one full point. And then at 0 is 0. Notice, one more time, that this function is between -infinity and -1, and this function is between -1 and infinity. Can anyone give us the range of this function? Okay, from below.
-infinity.
Correct. And 3 must be with an open, with a parenthesis, because it's an open point. Okay, so now we have a second piecewise defined function. Okay, back to lines. I'm looking at on page 268. Let's see what we. I'm hoping that you have this in front of you from Multimedia Library. The book is in my lab math. So I printed out just these pages with exercises. So 268. You don't have to print out anything as long as you have this, because I think it's difficult for you to see. Or I can bring it up and share it with you on the screen. It's up to you. You tell me what you want me to do. So we have a bar graph here. Gives the life expectancy for American men and women born in 6 selected years. So they selected 6 years, and they followed them throughout their life and their life's expectancy. You will use the data to obtain models for life expectancy, male predictions, and make predictions about how long American men and women will live in the future. So we are given the model in the sense that they plotted the data and they constructed what is called a linear regression. We don't need to know that part. So they constructed, they came up with the lines that fit the best the data that they had. So would you like to analyze life expectancy for men or life expectancy for women? So we have several questions here, one for male life expectancy and one for women. For females, which one would you prefer? Which one?
It doesn't matter to me.
I couldn't hear you.
They just said that it doesn't really matter to me.
No, it doesn't. It really doesn't. Okay, so let's look at problem 90. So it's 90 on page 268. Use the data for females. So females is this data shown in the bar graph at the bottom of the previous column to solve the exercise. Let X represent the number of birth years after 1960. So I take notes as I read. It says X represents the number of birth years after 1960, which means X equals 0 represents 1960. And let Y represent female life expectancy. Okay. Create a scatter plot they already did that. That displays the data as a set of 6 points in a rectangular coordinate system. Draw a line, they already did that. Through the 2 points shown for the life expectancy for 1970, we have it. 1970 and 2000. So years after 1980, or we can use directly the data, because I don't see here exactly what they are saying. 1970 and 1970 is 10 years after 1960. We can approximate.
I don't think that the line graph is that's percentage of marriage, not life expectancy.
Just the bar graph. Then we're going to use the bar graph. So 1970 and 2000. Okay, so for 1970, for females is 74.7, and for the year 2000 is 74.3. Am I correct? This is a little blurry. When you print it out from Pearson Ed, somehow it's a little blurry for me.
Yeah, it's 70 for the year 2000. It is 79.7.
For the year 2000, 79.7. Thank you. I looked at male, right? That's what I did. Okay, perfect. That's all we needed. Since we're talking about 1960 being x equals 0, we're not going to use the name of a year in an equation. We're going to replace it by 10, because it's 10 years later. For 2000, we're going to replace this by x equals 40. So therefore, we are given two ordered pairs. X is the, so also this is very important to mention, time and life expectancy. So this is the independent variable. This is the dependent variable. Because if I mess up the points and not write time, life expectancy, time, independent, and life expectancy, the whole thing will collapse on me. I'm not going to get anything. So 10, the first ordered pair is 10, comma, 74.7, and the other one is 40, comma, 79.7. Good enough? Nothing different from what we've just been doing. 79.7 minus 74.7 over 40 minus 10, which is 30. So let's see if this is an integer when we divide it by 30. So tell me what you get. I'm calculating it. And I got, when I divide by 30, it's better to leave it because it's 5 over, so I got 5 over 30, which is 1 over 6. This means nothing without the measurement unit. Remember, it's a rate of change. It has to have two measurement units. One coming from the numerator, the measurement unit of the numerator up here, and one, the denominator, coming from the measurement unit of the denominator. So this, first of all, is a positive number, and then we will give the interpretation to this. I don't care if they ask about that or not. This is very important to understand. So what is the measurement unit for the top? The measurement unit for the top is right here, life expectancy. Yes, it is in years, right? Life expectancy in years, and this is the birth year, so it's per year. So obviously the denominator is year. And this is the life expectancy in years. So how do I interpret this? And we're going to write one sentence together. According to the model, which we haven't determined yet, we have one more step to go. The female life expectancy is increasing from 1960 to 2000 by 1/6 of a year each year.
Wouldn't we say that it was increasing from 1970 to 2000 because the company was in it?
It was 70, yes, thank you. Yeah, I looked at the origin where they started. It's correct to say 1960, but no, I would like to just say exactly with the points that we used. Thank you. Yes. I looked at x equals 0 instead of 70 to 2000. Yes. We have not analyzed what happened between 1960 and 1970. We only analyzed from between 1970 and 2000. Thank you. Thank you. Correct. Absolutely. So, over the last 30 years, it appeared that the female life expectancy has been increasing by 1/6. It's not much, but still it's not decreasing. Increasing by 1/6 of a year each year. Okay, now let's find the model, because we haven't finished. So we'll be using y minus y1, of course, equals the slope times x minus x1, and I already have 2 points. I'm going to use this one, doesn't matter. So 10, 74.7, and 1/6. So then y minus 74.7 equals 1/6 and x minus 10. So y equals 1/6 x minus 10 over 6 and then plus 74.7. And we need to approximate that to see, because it's 1/6, it can stay, but here I really have to approximate. I don't like approximating, to tell you the truth, but so minus 10 divided by 6. Roughly 73. So y equals 1/6 x plus 73. So this is the model. Now, coming back to their notation, we can write e of x, because they wanted the y variable to be denoted by e of x. That's fine. That's not a problem. We can plot these points, put them in the graphing calculator, and plot the graph, because we didn't do that. I thought I was referring to that male female. I didn't look carefully. I thought it was right there. So we can do that. I don't want to skip it. So we can plot. So they are, for female, I think I see, is it 73.1? Yeah, so the numbers I think are 73.1, 74.7 that we know, 77.4, 78.8, 79.7, I think the last one is 81.0. So between 1960, 70, 80, 90, 2000, and 2010. Now the thing is, here we have to be very careful when we select the scale, because I have to be careful. I need anywhere between 70 and 85 if you want. I'm going to break the graph and say I start here at 70, and let's suppose we end here at 80, and the next one will be tiny bit, because they're quite close. So for 73.1, I'm going to say here. For the next one, 74, somewhere here. For the next one, 77, a little higher. This one, 78.8. For 2000, somewhere here. And then for 2010, somewhere here. So if I want to draw a line, I can't. I can draw a line that is the closest through them, but I cannot draw a line through all the points. That's not going to happen. So that is called, if you ever need to take statistics, this is what I teach my class on Thursday, I think. It's a linear regression. You do not need to remember this. Linear regression line. So we will graph a line that is the line of best fit. I could say that this is this line, 1/6x plus 73. I don't know though, because I have not made any calculations for that. So this is what is called the scatter plot. And then this is the linear regression line, the line that best fits the data. And with that, we answered. We'll have one more question. Use the function from part B, what we just determined, to project the life expectancy of American women born in 2020. Very good question. So we want now to predict 2020. So we know that x equals 0 represents 1960. So 2020 will be what? And that is the number that I will have to plug in. And you'll tell me what would you plug in.
I'll plug in 60.
So we will plug in 60. Very good. So we have 1/6 times 60 and plus 73. This is 10. So 83 years old. Or 83 years. You can put in your year when you were born. You don't have to tell me, but you can put it in according to the model and see according to the model. It doesn't necessarily mean that everyone will fit the model. According to the model, what is your life expectancy? Very good. Any questions? Any questions?